Hello, this is another chalkboard video. Today we're going to talk about inertia ramp. This is the second part as to what makes peak horsepower. The first part was average horsepower. So when we were talking about that, we looked at CFM and lift of the cam and where that basically puts us. Now the question comes up is, why is that number only 80% of what we're going to actually see in horsepower? And that's because the camshaft has an effect on how much of that airflow we're going to use. That's what duration does on a camshaft. Now, we have talked about camshafts before and the filling at 75 degrees after TDC. And that's a very important event. That's probably one of the most important events in a camshaft. You have to get that fill going correctly. Now, the second event that follows that that's important is really what controls your top end power. And that's the intake closing point. Now, the intake closing point is not really calculated at 50, but I'm going to give you an approximate so that you can understand it is. And then we'll probably do another video down the road of how to make that even more precise. But I'm just trying to get you within a few horsepower of what the engine will actually make. And the intake closing point is important. The reason it's important is because of how engines work. Now, I don't understand why everybody got hung up on the Helmholtz frequency thing. That is only, even if you use the first phase, that's only a few percentage points. I will probably do a video just on that, so I'm not going to go into it a whole lot. The main way an engine works is inertia supercharging. An object in motion stays in motion until acted upon by an outside force. That's basically the idea behind inertia. Once the air gets moving, it keeps moving, even though you don't have necessarily a draw on the cylinder, in order to keep filling the cylinder. Now, normally, when we talk about this, we talk about that in the effect that it could go beyond 100% fill. But in reality, all engines work on that inertia, and it's really somewhat RPM dependent. Now, as you extend this event out, as you move this event later and later, technically you're going up in RPM a little bit because you need airspeed to make it work. And so you start getting pulse back at really low RPM. And as you extend further and further out, that pulse back, that pushing back of the air, moves up in RPM. Now, a lot of guys will talk to you about dynamic compression, and I'm thinking we may have to do a video on that too. So we're getting a whole load of videos that I got to try and knock through. But for the moment, we're still going to talk about inertia ramp, and that's out of the Superflow book, which came with the flow bench. It was done, there was some testing done by a Japanese gentleman. I am not going to try and pronounce his name. I don't know if you can read it. It is in the Superflow book, along with a link to his ASE paper that he wrote about it. My Japanese is not that good, so I'm going to not even try and pronounce that. He did it in '79. It's paper, Society of Automotive Engineers, paper 790484. And it's also referenced in the book. So if you download the PDF of Superflow Flow Bench Handbook, there'll be references to it and a basic description of what I'm talking about, which may be enough for you. You may not need the paper. So anyway, it really showed how engines function. And I think a lot of people get confused because they don't understand what he was really talking about. So the main thing that I'm talking about about is the closing point. But it's not really about the closing point. Camshafts work from TDC down to closing, this whole sweep. And we've talked about 75 degrees. You got to have a good fill going at 75 degrees. That's the first thing you do with a camshaft, because OEs don't even come close to filling well at 75. That's why you can throw in a really little cam on a really tight load center and pick up a bunch of low end, because it's all about that 75 degree. But beyond that, your peak power, not your torque, but your peak horsepower, is really about this closing point and the duration it takes to get there. Because that's the total fill and how full the cylinder is going to get. Now, this is a dynamic thing. Like I said, it's RPM based. So as you go up, that's why it's high RPM. Not super high, but where your peak is going to happen is the upper RPM, and that's about this event. And that's because you need the airspeed to really make it work. As you go up in RPM, the airspeed in the intake keeps increasing. And when you hit a certain point, that's your peak RPM. That's your peak horsepower point. Now, you can calculate it with the closing over here. Just to put, this is trying to make it really simple. There is math, and I'll do a whole video on just finding it out. This percentage here, 85, 90, 100%, 110, 120, 130%, that is how much of this CFM you're going to use. And that really controls your peak. We got the number. You know, I came over here on the cylinder head in the previous video. We chose something that was like, it's 680 lift with a 1.6 rocker. We're at like 680 lift on example. I'm going to do another video after this one of a real world example of this. So this is the basic motor that I'm talking about. And it's 680 lift, and we figured out it was about 265 CFM. And so that's going to come out to 551 horsepower using our 2.08 horsepower per CFM number. CFM times 2.08 equals the basic. Like I said, that gets you about 80%. Well, that 80% is because depending on the camshaft, you could be above or below that. And that's really based on the duration and the closing point of the intake. So at, like, say, a 208 duration at 50, I only talking 50, remember. So at 50 thousandths tappet lift, if you're talking about a camshaft that's around 208, 210, a basic RV cam. I'm not going to start at OE, because OE, remember, has a terrible fill at 75, and you got to fix that first. So we're going to start with an RV cam. A basic little RV cam is only going to use probably 85% of that CFM number that you chose over here. Now, if you're talking about an RV cam that's like 500 lift, you know, that's 253 CFM. So if you look at 253 CFM, you can get a certain amount of horsepower. But then if you add in the fact that you are going to cut it short because it's a little camshaft, and you're only going to use 85% of that CFM, suddenly your 253, of which you're only using 85%, times the 208, which is your horsepower per CFM, comes out to 447 horsepower. And if you ever look, that is a very typical small block engine with a regular kind of head and a regular little camshaft. I mean, you're usually in the, 4 to 450 range, and that's because of the cam down here. Now, if you were to go up in camshaft size, you would gain horsepower. Well, that's based on a percentage. If you get up to like, 227, 230, and I'm giving you a range because some of it is valve size, some of it is ramp speed on the cam. A faster ramp speed will actually move this closing point out a little bit. And so like a roller cam, that's part of the reason they do better. So I'm giving you a bit of a range on these. And like I said, we could do another video on more exactly how to get that number down to really accurate. But you want to just get pretty close. And this gets you pretty darn close. So if you're up at like 227, 230, then you're going to use like 90% of your flow. As you get up to like a 256, 260 cam, you're going to use 100% of your flow. And this is why a lot of guys tend to like camshafts that are up in that range, because that is letting them use all of the flow. Now, like I said, basically we're cutting off the flow. I mean, we're talking about less than what the head actually flows. Now, at really low RPM, kind of below where you'd even dyno test, I mean, because dyno testing, usually you're at 3,000 and up, or more. You may even start at 4,000. And so we're talking about way low RPM with some of these cams. It will affect it. You run a 256, you're going to have some overlap. You're going to have a little bit of pulse back at low RPM. But by the time you're running a 256 cam, you've probably got a little bit of converter in the car, and you've probably got a little bit of gear in the car, and you're running a little bit more camshaft, and that puts you in a nice sweet spot. That makes it easy. Now, I know you're thinking, oh, well, wait a minute. Can I get more? And the answer is yes, and it happens all the time. Now, when you get into big race motors, especially drag race motors, where lots of converter, lots of gear, you're not worried about drivability, you're not worried about that low RPM pulse back. Because, I mean, if you ever look at the John Cossey clear intake video, which you might want to look up if you haven't seen it, that shows pulse back. I mean, it's actually pushing back. That's a really big cam at lower RPM. That's what he's actually demonstrating. So as you go up to like 278, 284 cam, somewhere in there, I mean, by the time you get up in these, you're really talking roller, solid roller. So, I mean, it skews the duration a little bit. But then you're going to get like 110% of the flow. You start talking like 294, you can get 120%. You start going up, remember these are at 50, these are big cams. You start talking, maybe 306, 308, you'll get like 130% of the flow, if you can pull it off. Now, this curve is kind of drawn like it is for a reason. This is an exponential curve. That means that for every little increase you do, the gain grows dramatically. But the problem is, so do the problems. As you push this event further and further down, you're going to get more and more pulse back at lower RPM, and the airspeed in the intake better be in good shape and actually pushing well, or you're going to be way up in RPM to get that airspeed. And so this takes a little bit more to work and starts dramatically affecting your low end power. That's why 256 tends to be the sweet spot, 260 for guys building engines. They kind of like that little spot because it gives them a lot of power, but they don't have a lot of trouble, and it kind of just runs. And so most of you are going to be down here. Now, that's really only about 15% change in power. So, like I said in the previous video, the biggie about getting air in the motor is CFM and your lift. So that really is the first dictator. That's why it's 80% of what you're going to make. And like I said, for some of you, that number alone is probably close enough. And then this will say, well, we're going to probably lose a little bit, or if you're running a bigger cam, you know, maybe we'll be right at that number. So that's how it goes. Now, in the case of this particular motor, which I'll talk about in the next video, I actually figured out more accurate. Now, this is called the Z of a camshaft. And there's a chart and there's information on it in the Superflow book. So this isn't something I made up. This is just something I sat down long enough with to understand. And there are mathematics involved, and I'm trying to eliminate those just to give you a really general understanding of how the engine works. You know, the number you're going to get, you know, is not going to be perfect, but it's going to be close enough that you really have an idea. And most guys, it's like, okay, I need to build a 500 horsepower motor. I need to build a 550 horsepower motor. They have some number in their head. You know, I only need a 450 horsepower motor. What do I need to do that? And this will get you there pretty quickly to know whether or not you have a choice. Now, in the next video about real world, not only am I going to show how these numbers actually work, but I'm going to talk about some real life things that can happen that can affect the number. I mean, this is kind of your ceiling. This is the most you can make is once you figure out the camshaft, it's going to give you the limit of what the motor can actually do with that cylinder head and that camshaft. And then the question is, did I mess up? Am I running the wrong carb size? Is the intake a problem? Is there other issues causing me to not make that horsepower number? So we will talk about that in the next. But basically, it's CFM is the most important at the lift of the camshaft, which gives you a basic idea. And then the camshaft duration, which gives you a percentage or a Z of how much of that CFM you're going to use. So remember, you know, a little RV cam, you're going to be at probably 85%. You know, you start talking a 230 cam, you're going to be at like 90%. You can split this. You start talking like a 240 cam, you might be at, you know, 94, 95%. By the time you get up to 256, 260, depending on the ramp profile of the cam, you're going to get probably 100% of the flow. And you could nudge just past that a little bit, you know, run a 264, you know, and that's basically what's up here. He's running a 260, and so it actually comes out to 104%. So his ceiling is going to be 573 horsepower. But I'll talk about more of that in the next video. So I wish you luck on all your stuff. That's basically where peak horsepower is generated from. It's an inertia ram principle, which is really how engines work. And I wish you luck on all your projects, and I'll talk to you in the next video.